Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to look at a pretty thorough example about solving ax equals 0 so that we can find out what the null space of A is. And on the screen right now, we just got done proving that the null space of A was and is in fact a vector space. So we're going to go get some fresh piece of paper, and let's take a look at an example. So this is an example that you can see done also by our author, but it's such a good example that I figured it's worth using again. So here we go. We're going to begin with let A be the matrix of 1, 2, 2, 2, 2, 4, 6, 8, and then 3, 6, 8, 10. Okay. And our goal is we're going to find the null space of A. And we're going to use our new notation. N of A means the null space of A. So if I had a matrix B and I wanted to find the null space of B, I'd write N parentheses B. Okay, so we can use that notation is fairly versatile. Now let's do this. Well, remember this. This is the null space of A. Let me write some of this. The null space of A are the x's that satisfy A x equals 0. That's a 0 vector. So I'm going to show you a few things on how we're going to work with this. The first thing is, let's just write the equation. If I was to solve this, really what I'm solving is 1 by rows here, 2, 2, 2 times 2, 4, 6, 8. And the third row is 3, 6, 8, 10. And then let's write out x. Notice that I have 3 rows. So in this case, the rows is m is 3, and the number of columns n is 4. Well, it's the number of columns that indicate the number of components in our vector. So x in this case has x1, has an x2, has an x3, and an x4. There's 4 components. Equals, and then this is the 0 vector. So here's a good question for you. Before I write this, how many components would be in this 0 vector? Would it be 3, like the rows of A, or would it be 4, like the number of rows in X? And the answer is, remember what that 0 is. It's a linear combination of the columns of A. That's what it is. So in other words, if the columns of A are vectors with 3 components, our result, the 0 vector we're looking at, has 3 components. Okay. Now, when we've solved this vector, or this matrix equation, what we did is we made the augmented matrix. We made the augmented matrix of 1, 2, 2, 2, and then we didn't worry about the variables because they never changed. So then what we would do is we'd put a vertical line, and then we'd put the B matrix. So remember, if you think of this as A x equals B, in this case B is 0. So then we'd write our augmented matrix. Let's keep going as 2, 4, 6, 8, 0, 3, 6, 8, 10, 0. Okay, and that gives me my augmented matrix. Now, when you're solving AX equals 0, when AX equals 0, it doesn't matter what row operations are performed on A. The row operations here, we're going to, because we want to take A to U, and today we're even going to take it to R. Yes, a new matrix. But it doesn't matter that if you take twice for example, if we take row 2 minus 2 row 1s. Well, notice this. So let's just write this result. Let's write this result over here. Well, this would give me the new matrix of 1, 2, 2, 2, 0. And then 2 minus 2 is 0. 4 minus 4 is 0. 6 minus 4 is 2. 8 minus 4 is, oh, whoops, I put a 4. That should be a 0. I'm sure you didn't do that. 0. And then notice this. In the right-hand column, if I take 0 of row 2 and I subtract 2 zeros from row 1, it's still 0. And then my third row remains unchanged. 3, 6, 8, 10, 0. So the point is, look at this. By doing row operations, when we're solving, this only works for when AX equals 0. But the row operations, let me write that. Row operations do not affect B when it equals 0. And so what we'll often do is our augmented matrix, so for AX equals 0, the augmented matrix the augmented matrix is A. Yeah, we don't even, in the same way we didn't write the variables because nothing changed with our variables, nothing changes with the 0 vector. So usually we just work with A, and you just need to keep in mind the context with which you're working. I know this subject is very context-based, but that's what the context of the problem. All right, so let's continue this. We've taken A, we've done one row operation. I'm going to do another one, and I'm going to make a yellow comment, just insert here. We're going to work on row 3 by subtracting 3 row 1s. Okay, I'm going to bring that result down here, and I'm going to have the first row, 1, 2, 2. I'm going to write this in my new augmented matrix now, 2, which means I don't have to write the fifth column. And then I have a 0, 0, 2, 4, and then I have let's see, 3 minus 3 is 0, 6 minus 3 times 2 is, that's 0, 8 minus 6 is 2, 10 minus 6 is 4, and, oh, we're getting there, But notice this, something strange happened here, something a little different. Let's make note of this while this is hot. First off, here, the 1, this was our first pivot. But then what happened? Well, normally then, our pivots would go down the diagonal. Well, look at this. We've already got, there's a 0. And there's no other way we could get a non-zero number in that position. So what we do is we just go over to the next non-zero in that row, which happens to be this 2. So this 2 is now, that 2 becomes our second pivot. So that 2 right there is now our second pivot. All right, so if that's the case, then what we do is we need to use that as our pivot, and we need to work on the 2 that's below the 2. So we're going to work on row 3 here. So row 3, and I'm going to do that by subtracting a row 2 from it. Let's see what happens. So I subtract it from row 2, and I have 1, 2, 2, 2. That's my first row. My second row remains unchanged, 0, 0, 2, 4. And my third row is 0, 0, 2 minus 2, 4 minus 4, and we're done. Whoa, this is totally new territory. We have a row of zeros. Now this, we are at the matrix U. This is, and it's, it's as upper triangular as this matrix can be. But that's where we're at. We have our upperish triangular matrix. And but we're going to go a little bit further. We could solve it at this point. We could solve it at this point if we wanted. But today we're going to go even further. And we're going to go further in the same way that we did when we were finding the identity matrix. So what our next step is I'm going to copy this U. I'm going to bring it down. We're going to start on a new piece of paper here. We're just going to go fresh, I think. Yeah, just a fresh piece of paper. There's our U. And we're going to take U to R. And what R is, take U to R is called the RREF of A. And RREF stands for reduced. Let me write that down here. That's a big one. It's reduced row echelon form. Okay, that's what RREF stands for. Now you can see why there's an RREF. And then the reason for RREF is some calculators have that as a function that they can do. They can find RREF rather quickly. Now, here's what we need to do. So what we need now is we need all. So RREF has all pivots. All pivots are one with 0. How about zeros above and below? Well, obviously we've been working on below. We've already done that, but now we're also going to have zeros above the pivot. So I should have maybe changed the order below and above. But makes sense. Here we go. So what are we going to do to U to accomplish this? I think I'm going to write this in yellow for my next step. I could just, and I'm going to work on, notice this. So we said that 2 is the pivot. Now, the next pivot, there's no more diagonal. 0 can never be a pivot. So 2, which was the pivot, our last pivot, it's the pivot. 2 is the pivot again. Okay? So if that's my pivot, then I need to look above the pivot. And I would remove that 2 above it by subtracting row 2. So let's do that. So we're going to work on row 1 by subtracting from it row 2, and that would be a 0. So let's write our result. Our result is now 1, 2, 0, 2. And, oh, nope, minus 2 because we had 2 minus 4. That's a minus 2. Then we have a 0, 0, 2, 4, and then a row of zeros. Okay. And then our last step that at this point is this 2 needs to be a 1. Remember, that was one of these little pieces that we said. All pivots are 1, so we need to change our pivot here to a 1, so we can do that. Sure, of course we can. We can do that by taking 1/2 times row 2, and our resulting matrix is now 1, 2, 0, minus 2, 0, 0, 1, 2, and then we have a row of zeros. And it's this matrix here that we need to stop and take a lot of looks at. A lot of looks. So it's so important that I'm going to copy it and move it back up to the top of the page. Oh, whoops. Let's undo that. And let's grab the scissors and do it this way. Be more careful. Yeah, let's probably put it about Probably about there, because we need to talk about this thing. All right, notice this. So pivots in columns 1 and 3. Columns 1 and 3. So here we go. But notice this, that in column 2 and column 4, I don't have a pivot. So what we would say is column 2 and 4 are free. Yeah, are free. And we're going to show you how that works, how it applies. Columns 2 and 4, or columns 2 and 4 are free. Now another thing is the number of pivots is called the rank. It's called the rank of A. So in this case, our rank R equals 2. It's the number of pivots. The number of pivots is R. R is 2. Okay. And I'm going to pause here for a moment. Okay, I'm back. Now, also, and look at this. So if my rank is 2, then what I can say is that the number of columns, so the number of columns, which is n, minus the rank is the number of free columns. So in our case, there was 4 columns, there are 2 pivots, a rank of 2, and so we would say that there are 2 free columns. Okay. I think we're ready now to find the solution to this problem. Let's find the solution to this problem. And how it works is actually I think it's pretty incredible. So let's write it. Let's write this. Okay. So again, I'm going to copy this matrix, and we're going to bring it down to a new page. Oh, heck, there it is right there. Let's just go straight to that one. We'll just go straight to this one. So remember that is the matrix A, or now it's, that's what I wanted to say up above, is this. So we've taken A to U, and then U, and we finally ended at R, reduced row echelon form. All right, there's our matrix R, and let's use R to write our solutions. So I'm going to come up here. Here is our, that's going to be a bad reference. So let's just copy R. And let's just bring it down. And we'll use it right there. Okay, so how do we write this solution? How do we do this? Well, let's just remember what this problem was. This is the problem of x1, x2, x3, x4 equals 0. Well, let's just write our system of equations. Our first equation says that 1x1 plus 2x2 plus 0x3s, I'll write it this time, minus 2x4s has to give me 0. Okay. The second equation that I have, I'm going to leave some space. The second equation says that 1x3 plus 2x4 equals 0. Now you might have wondered, well, why did you leave that big space in there? And here's the reason. Notice that when I solve these, what do we say? There's no way to solve directly for x2 or x4. So not only that, so these free columns, so let's make that note, free columns. And I'll show you how that works. Free columns create, or give rise to, create free variables. Free variables. How so? Well, notice this. Let's solve this first equation for x1. If I do that, I have x1 equals minus 2x2 plus 2x4. And let's solve this second equation, x3 as minus 2x4. Well, wait a minute. Now x1 and x3 are both based on x2 and x4. There's no way I can pick, or there's no way I can solve directly for x2 and x4. So what do? We choose values, but we choose wisely. So now because they're free, we choose our free variables. Oh, I'm sorry. Let me go back. I want to show you how that gives rise to this. So let me do this. Well, what do we have for x2? We have just that x2 is just x2. That's about the best we can do. And x4, there's no direct equation, so I'm just going to leave it as x4, and we'll write these are free. Free. Now, well, what did we say? So what we said is that the vector x is equal to, and let's write out the problem. It's equal to x1 and x2, x3, and then x4. Okay, well, look up above. Looking up above, we have x1 is minus 2x2 plus 2x4. We have that x2 is just x2. I'm going to line these up. We have that x3 is minus 2x4, and we have x4 is x4. Well, this is the sum of two vectors, of which one vector has x2 as its common component, and the other one is x4. So let's break this up. This is minus 2x2, x2, and then I don't have any x2 in the third or fourth component, plus, then I have 2x4. I don't have any x4s in the second component. I have a minus 2x4 in the third component. I have x4 in the fourth component. All right, now we can factor out those common scalars. This is x2 times minus 2, 1, 0, 0. Plus, I have an x4 times, let's see, a 2, 0, minus 2, 1. Wait, that's it. That's the solution. That's our solution. So what does this tell us? Well, this tells us a lot. It tells us that the general solution, or no, don't want to write that way. How about x is a linear combination of, and I'm going to call these we used this earlier, S1. S1 is my special vector, minus 2, 1, 0, 0. and S2, which is 2, 0, minus 2, 1. Whoa, that's it. X is a linear combination of those two vectors. Well, if you have two vectors and you take all possible linear combinations, that is, this space is a plane in R4. Notice that the columns were in R3, but the null space is in R4. So it's a completely different space. So that's what it is. It's a plane. And so we could just write our solution. We've already written it once as x is just some scalar c times s1 plus some other scalar d times s2. We'll say that. So c, d are scalars. And that's how we find the null space of the matrix A. Trying to think of any last minute thoughts. I'm going to check my notes because make sure I did everything that I wanted to. There's one more thing though that I wanted to show you, and that is this. We solved, and what we did is we found the null space of A. And then what we did is then we took A down to U, and then we took U to R. Well, along this path, what we were solving for was the vector x times that matrix would give us 0. And the x part and the 0 never changed. So in the end, what we can say is that the null space of A is equal to the null space of U, because they're always just equal to 0. The right-hand side never changed. It's also equal to the null space of R. And there we have it. A few last considerations then is when, when A is wider than tall. And when does that happen? It happens when n, the number of columns, is greater than m, the number of rows. Then A has at least one special solution. There's at least one special solution. That helps. Thanks for watching.